Please welcome Professor Tomiyama.
Good afternoon or good evening, difficult timing. Ladies and gentlemen, I'm very much honored to be here to deliver my speech. This is not meant to be very serious. Of course it is serious, but I mean academic, serious talk. So please stop me whenever you have questions and if you want to discuss. And since this is the Systems Center of Bristol University, I thought it might be interesting to discuss some of the things I'm thinking about systems. So now this is how I begin. Modern products are increasingly complex, and one of the reasons, there are many other reasons as well, of course, is multiple acts, multiple disciplines, multiple stakeholders, multiple goals to satisfy at the same time. And I believe one of the most fundamental reasons for this complexity is multidisciplinarity. And this is the reason why we need systems approach. Of course, this is systems center, so you are all aware, conscious about systems approach. So I don't have to tell you about what systems approach is and how you can tackle systems. But if you go outside this building, sometimes what happens is people simply forget or neglect or give minor role to systems approach. Although in many cases, what you are designing is actually a system or very complex system, not a single component. And even a component design, you have to think in the context of systems. So what is important is systems approach, systems thinking. Although actually, well, if you look at many universities, education, systems element is very small, especially in undergraduate education. And this is true that was true in Tokyo, that was true in Delft. And if you start teaching systems, a lot of people think it's not even engineering or science. So today I would like to challenge you. This is how I think what system is, and this is my approach. And my approach is, okay, let's think about architecture. Let's put the architecture in the center, and this is how you tackle the systems. And architecture is again a difficult word because systems is also a difficult concept, but architecture is even more difficult to understand at least, and it may confuse people. But what I think architecture is something about integration of cross-disciplinary communication and a mutual understanding of stakeholders. And this is where you talk about system. You talk about systems in terms of function, behavior, state, structure, organization, you name it. This is the place where you can talk about the system as concrete, living thing. Now, in my career, you said 30 years of my research career, and I was kind of shocked because I never thought in that way. I have been doing things in a completely wrong way, probably. This is traditional science or scientific engineering. You discuss products, you discuss components, you discuss concrete phenomena, physical phenomena. Most of the time you deal with analysis, analyze the performance, analyze the whatever features, and you, in order to analyze, you have to be an expert in monodiscipline. In my career, I have focused on processes. I have focused on the systems side. I have focused on rather than concrete phenomena, abstract concepts such as architecture. And I have discussed synthesis, and I try to be multidisciplinary. Now, these 5 things are completely different or opposite to traditional scientific approach to engineering or design. And this is why probably I'm kind of exceptional in the sense that I do not really find a place to live. Now, modern products, well, you can think about robots, you can think about, this is, well, these are more or less what I think complex products. This is a semiconductor manufacturing machine, stepping machines. This is the Prius. It is a complex product. It is complex in the sense that it has 10 million lines of source codes besides MATLAB generated codes. So they use both hand-woven programs as well as MATLAB generated codes to do some very simple things. And in total, they have 10 million lines, at least hand-woven, handwritten codes, source codes. Airbus, well, built here, probably. And this is the size of complexity, probably. And today, just about now, I think the Apple is now announcing a successor of this model, but okay, this is still complex. And this is one of the companies I was dealing with, having projects with. That's very professional, fast speed, color printers. Now, that's another example of complexity. And this is another company I was working with, and I really wonder if this guy can fit into this machine, but obviously he does. Now, these products are more or less called mechatronics products, or someone say cyber-physical systems, or, well, from software's point of view, embedded systems. And they are complex because they are multidisciplinary. And of course, in a classic sense, it contains a lot of components, subsystems and components. The size-wise also extremely big or extremely small. The accuracy of these stepping machines are nowadays, they are talking about 14 nanometer rules. So the stepping machines have to move to have accuracy, repeating accuracy of that level, 14 nanometers. That's the size of circuits. They have very complicated phenomena, behavior, non-linearity, of course, and moving targets, so it's not really clear what you are looking at. And the constraints are also changing dynamically. And these products are usually discussed in the context of product service system. It's not just product, meaning, well, we have a lot of stakeholders around the product. And of course, we have to nowadays think about sustainability, corporate social responsibilities, working conditions, etc., etc., etc. And because of this, products are becoming very complex, and standard number of details is about 10 million. So as I said, 10 million lines of code. If you look at the geometric features of standard passenger car, it goes up to 10 million, because you have 10,000 components. 10,000 components. Every component has, well, let's say 1,000 features. Then it becomes 10 million. A380 has 6 million unique components, something like this. So this is about the size we are now dealing with. Then at the bottom, we have many different disciplines which can deal with this size, number of details, like mechanical engineering, electrical engineering, electronics, systems engineering, production technologies, and blah, blah, blah. But these are all monodisciplines. Despite the size of these details, we can still handle this size. The reason is simply we have computerized tools. Now, the top level is probably we have complexity of maybe 1,000 details. That's the functional top level. And you go down to the systems level, middle level, which is multidisciplinary, and subsystems level. And then you go to the component level. So the thing is, the bottom line is very complex. The top level is, in a way, simple. We can handle. Toyota says you can put all the top level things in one A3. A3 is a magic number, and I found out why A3, horizontal A3. A4 is if you have 10 to 11, 12 point size, A4 is, if you put it in vertical way, is actually the maximum size of piece of paper you can handle. Because you have two eyes, usually, you can deal with 2 pages. And therefore, horizontal A3 is the maximum size of paper you can handle. You should be able to put with 10-point font all the information at the top level, whatever you have, in this A3 format. And that's what Toyota says. I don't know if it is really true or not, but it looks like that's the level of details you can deal with. Now, having said this, top level is 10,000 detail at the moment, 1,000 details, and that's what you are dealing with. And then you break down, you go to 10 million. Right. What are we going to do with the middle layer? Somewhere between 1,000 and 100,000. We really don't have tools in this level. Systems, middle, multidisciplinary subsystems level. And we do have problems here because subsystems are fighting each other, interfering with each other. On the other hand, multidisciplinarity is source of innovation. We know that. It will increase the added value because we may have better functionalities, performance, and quality, and we can have cheaper cost price. In dealing with multidisciplinarity, and innovation. Well, the easy way, it's not easy, the most difficult way to have innovation is probably discovery or invention. So you have a new field somewhere between existing field or new some known things. So you have an invention. You can also think about deepening. So you have one field and you go deeper, deeper, deeper. And this is very normal in science. But you can also think about integration. So it's combination, new combination. When Schumpeter, the Austrian economist, invented this concept of innovation, he simply meant new combination. So new combination of materials, new combination in way of working, in new combination of market and new market. And that's what he meant, innovation, not necessarily new invention. So integration, new combination can lead to innovation, and this is how you deal with new thing. Having said this, at the same time, multidisciplinarity actually increases the complexity of the product development processes. We have to realize that, because interactions among subsystems and the components can easily happen. Stakeholders, we have many stakeholders, but they do not necessarily understand each other. And more importantly, the fundamental problem we see is many engineers are actually trained, educated in monodiscipline. So you are a mechanical engineer, you are professionally established as a mechanical engineer, for example. You belong to the Society of Mechanical Engineers or Institute of Mechanical Engineers, and you have less interactions with other people. Now, this will create, of course, professionally problems, of course, sometimes, because you don't understand what other electronics engineers are talking about. What software engineers are talking about is not necessarily understood by control engineers. So this is multidisciplinarity could be source of the problems. Having said this, how do we deal with these systems? How do we deal with these complex systems? The first thing we are told to use is divide and conquer. If it is a complex, big, huge system, yes, you have to decompose it into sub-problems, subsystems, sub-subsystems, sub-sub-subsystems. At the end, you arrive at manageable problem, and then you solve it, and then you come back, you integrate everything. This is how you solve the problem. You can also divide the problem into different processes. But if you have multiple processes, then you would like to have, if you have sequential processes, then you might not be efficient. So you like to have some concurrency. That's concurrent engineering. If you have good divisions of the problem, you can rely on good, commercially even, developed computer-based tools. We have many sufficiently capable systems nowadays. However, if you look at any of those systems, actually do not address integration as their strength. That's another problem. But still, we have good computer-based tools. So we even hear model-based systems engineering, as opposed to code-based, as opposed to document-based. We build models of the target system, and then this model can be directly simulated, directly verified, and you just build it. Now, the arrival of 3D printers is now really helping you to do that very quickly. This is where we are now standing, and this is how we reduce the complexity of complex systems. Now the question is this fundamentally a good approach? Traditional divide and conquer has begun with this guy, Julius Caesar, and he said that in his essay or diary, basically, during his campaign in France and in England, and he was dealing with these people. I don't know, in England, in UK, asterisks and obliques are famous, yes, very famous. So you see somewhere Caesar is sitting, I think. Here he is, yeah, he is sitting here. And but what Julius Caesar was dealing with are these people, and the problem he encountered was simply pure sheer number of these tribes. At that time, he had Roman soldiers, one legion of Roman soldiers was 6,000 soldiers, with 60 centurions. So one group of soldiers was 100, and at most one legion was 6,000. If there were 100,000 of these tribes, then he had a problem. Of course, with only one legion, he couldn't do anything. So he said, divide and conquer. Divide all these tribes into smaller groups. Never make them merge into a big group. Then because he is going to have a problem. That's how he said, divide and conquer. But this assumption actually fails against complex systems, not against complex systems. There are assumptions. We should be able to, when you are dividing, you should be able to see clearly defined systems component boundaries, subsystems boundaries. Subsystems should have minimum interactions with each other, except for those official boundaries, interfaces, and each subsystem should be easy to conquer, of course, easy to solve. This is the assumption. But we realize we have fundamental problems here. Methodologically, we really don't have established methods for subsystems decomposition and interface definitions. How do you do that? If you're given a task to design an aircraft which can carry 1,000 people, how do you divide it into sub-problems? What would be the sub-problems? If you have subsystems already, then the rest of the job is actually integration. But even then, integration is a big problem. if you have a very big system, usually it goes beyond perception of any human being. If you have 10 million components, if you have 10 million lines of source codes, no chief engineer can understand any details sufficiently. So that's one problem, and overview is often lost. You are working at the very bottom, but you don't see the whole system. And that also means you have problems with traceability. And often we divide the system into discipline-wise. Each discipline has its own decomposition. So mechanical engineering, assembly, production has its own decomposition. And that could be different from control engineering decomposition. And that could be different from circuit-wise decomposition. That could be different from whatever other systems decomposition. Structural engineering decomposition. So unexpected interactions among subsystems or sub-processes. Cross-boundary problems pop up at the integration. At the end of the day, what you get is messy so-called architecture, which is not really scalable, which is not really changeable. We have more and more in complexity. And in the context of multidisciplinary problems, systems, each discipline has its own decomposition. So every decomposition has its own language. They speak one language, and that means you have communication problems. And this is what is happening in large-scale, complex systems product development. Now, we often say process-wise, concurrent engineering is the way to go. You have to understand the top-level customer requirements, and you shouldn't do this because once you realize the problem at the very last stage, you have already spent a lot of resources. So what you do is, rather than going sequential, try to front load everything and overlap many activities. That's what we are told to do. But simply because of this complex nature of the product, communication problem happens. So still, communication is a big problem even you employ so-called concurrent engineering. V model is a famous model. So you have predicted model, and that's the implementation. You decompose the whole system into subsystems and try to implement and then integrate. Yes, that's nice to say. But the reality is, since there are so many problems, systems architecting, at the end of the day, receives very minor role. In fact, there are so many problems you find at the integration phase. Relatively, architecting phase becomes shorter and less important. So systems definition is often 1 month at most, and component development is technology development is something like 2 years. Integration 4 years. So what is happening is V model becomes tick model. Everyone wants to go to implementation phase as soon as possible, and at the end you find a lot of problems that could have been avoided if you have spent enough considerations, thinking at the decomposition phase. But that is too late. Another problem I see is in industry is no thorough requirement analysis, no functional design. Everyone thinks that we know functional requirements. It sounds very simple. It sounds very easy to do. So everyone thinks they mastered everything. But in fact, at the end of the day, what you find out is the component, the subsystem, and the whole system doesn't fulfill the functional requirement. Why? There was misunderstanding rather than technology insufficiency or immaturity of the technology. Sometimes you didn't understand interactions of subsystems. So the behavior of the whole system is completely different from the sum of subsystems. Subsystems behavior. And that is one of the biggest, one of the reasons for extended product development period. Basically, functions are rarely discussed. Conceptual design to design at functional level doesn't exist because of time pressure. Maybe you think we are redesigning the old product, so we don't have to establish a new functional structure, which might be true, but you are still introducing new functionality sometimes. So you don't realize that you change the functional structure, behavioral patterns, phenomena. At the end of the day, that becomes a problem. Formal function modeling is not used in industry. Well, very rare, actually. And if you say functional representation, it boils down to an Excel sheet, which is just a collection of requirements. And even that sheet will be stored somewhere in the knowledge management system and will not be opened until the design review. And someone opens that just one day before the design review and finds out that, oh yeah, something has changed. We don't satisfy this. So what I would like to say is, it is very important to focus on what I call architecture. Architecture-centric product development. And it has to be model-based, yes. But in model-based engineering, there's no architecture. So you have to introduce the concept of architecture into model-based engineering. How do we do that? Systems architecture is all about functions plus behaviors. When IBM invented the word systems architecture, when they were developing system at that time 360, 70, I guess 360, no 70, yes, 370 was a virtual system, virtual machine. It's called virtual system. So they had to introduce the concept of architecture. And operating system had to have architecture. And what is architecture? It is not just static structure only, but it came with dynamic behavioral descriptions. And we, in developing mechanical or mechatronical cyber physical systems, we don't have that level of descriptions yet. In software engineering, yes, we have static model, data architecture, data structure, data models, plus behaviors. But we don't have that in physical products in the equivalent level. So we have to be able to describe functions, we have to be able to describe behaviors, and we have to be able to add structural descriptions all together in one place. And that's what constitutes architectural description. If you have good architectural descriptions, architecture, you should be able to integrate different models, because architecture is a higher level view to represent the relationships among different models, different aspects. And it tells dynamic relationship, static, not only static, but also dynamic relationships among models. How those subsystems will be related or should relate with each other. And that's what architecture describes or defines. So architectural model plays a central role. You need to have architectural level models to decompose the system, and that's where you have to use your decompositional techniques. You have to describe behaviors, interface definitions, and that's the level you define how you integrate the systems. You need to have facilities to store information about the system architecture and different levels in different views. And you should be able to link and feed appropriate data for verification and validation. Store information about reference architecture and define and manage architecting processes. These are the roles that architectural models should play. And it should be based on some ontological system. It doesn't have to be this particular system, but should include functions, behaviors, state, transition of states, entities, structural relationships, that sort of things has to be in the one description. So kind of SysML type language would be appropriate, but SysML has some problems with representing functions or behavior, so probably you have to extend that. And this is something what I have been, our group, especially in Holland, worked on in architecting related work. So we tried to develop a computer-based tool at very high level description, try to describe systems in reference to users' workflow, systems architecting tool, decomposition tools, description models, and systems which helps you to detect unexpected interactions among subsystems. Well, anyway, these are possible, and I'm not saying that you have to use these, but most important thing is complexity management is actually the core of complex product development. And to do that, we need architectural level. We have to put the architectural descriptions in the center of product development. And you have to be able to use not only your own discipline, the knowledge of your own discipline, but also apply knowledge from other disciplines without big problems, difficulties. And for that, you have to have good understanding of other disciplines. So that's the communication basis, and this is the architecture. Okay, so this is what I have prepared, and hope you have some questions and discussions. Yes. Thank you very much.